Greetings. Welcome to ETAP Digital Twin presentation. My name is Farouk Shuku and I'll be introducing the ETAP platform and how it would work out with different solutions of ETAP. We are ETAP, the world leader in power system energy management and design from design to operation. We cover different sectors: generation, transmission and distribution, transportation, industrial, renewable, and mission control, and any other system from AC to DC, from high voltage to low voltage, and any kind of configuration that exists. We have been in this business for the last 35 years. We have supported more than 50,000 engineers throughout this period of time. We have over 100 plus quality assurance audits since we are a nuclear grade product. And we have been in many countries and many solutions that we provide, over 150 of them, with so many digital transformation. But the most important thing is that we have been keeping more than 98% customer satisfaction throughout all this time. The digital twin is a centralized concept, which is a platform that supports from modeling to visualization, from design and analysis to monitoring and prediction of the behavior of the system, to operate and optimize the system, and automate and control the system. Digital twin platform journey starts with modeling, visualization, analysis, optimization, monitoring and prediction of the behavior, and automation and control of the system. The first two portions of the system is design portion, which has to have automation knowledge to be effective throughout this whole journey. The operation and automation that includes the design all the way to automation has to have the entire design knowledge throughout this process. Goals of ETAP Digital Twin Platform are to support hundreds of intelligent solutions and to make power system efficiently and fully sustainable, and manage it throughout the entire life cycle of a power system, one of the most complex in all the engineering disciplines. So if you start from the past to present and future of any system, we have to learn from the past, understand the present, and predict the future. And this is a living, multifaceted digital twin platform that I'm going to be introducing to you. This platform was designed a system that can do model of all power system elements and connectivity, be able to manage the system and changes from the past to present and future modifications, include equipment data, old, existing, and new data with engineering data that is different than the existing one. Archive data from design, operation, and maintenance purposes for different visualization, and status of the devices can be different from design. Many of the configuration during the design and the real-time operation and configurations are different than the design configurations. Next is loading and generation for the design phase and real-time operation and archive data. Then we have analysis and optimization, which predictive design and predictive of real-time data, and also to be able to repeat all of these with the click of a button. Let me start with a flat digital twin platform for power system, a single record database with one set of data. By realizing a power system database consists of the engineering data, consists of generation values, consists of loading values, consists of the status of the equipment, consists of the state of the equipment, consists of service conditions of the equipment, the view and visualization, and also analysis. So with all of these, you can see for doing the different type of design and analysis, you would end up with hundreds of copies of a database for different modification and status and so on. And just imagine how much of a nightmare it is to be able to handle these multi copies of a same project and making sure they're all in sync. And if you change one, you have to change the other ones. Now in ETAP, we have designed a system, a platform, which is multi-dimensions, multi-layers, multi-disciplines, multi-applications, and it's time series. And that's what it took us so many years to develop this in beginning of 1990s, and it's been polished, it's been enhanced throughout the years, and now is a system that once I explain to you the capabilities, you would not be able to live without it. So a multidimensional database was designed and developed specifically for power systems. And it's very hard to actually show the multidimensional database on a flat 2D view. So we're kind of coming out with showing this in a different way. By doing this, I'm showing you 6 dimensions of this database. And these 6 dimensions are all orthogonal with each other. That means they're independent of each other. So the first dimension is called revision data. And that includes engineering properties, electrical, thermal, mechanical, physical, ratings, settings, and so on. And they change over a project's life cycle for different modification of the system, for different addition to the system. So we have one of the dimensions is this engineering properties. And it has multiple layers, unlimited multiple layers, and we call that revision data. Revision data, the purpose of it is to track and manage project lifespan from conceptual design to get approval, design, optimization, building, and commissioning. And this would be not just one project, because that's maybe that is the existing system, but the projects happen to come in at different time, and there are some projects that they have things which are similar to each other, common to each other, and those are we call group numbers. And then you have project with multiple stages, multi-phase projects, which phase 1, phase 2, and so on. And these guys would also have different things which are common to each other. For example, if you have a 150 horsepower machine that needs to be changed for one project to 250 horsepower, it also be common to another project that also needs a 250 horsepower. So the concept of group numbers and change numbers, in addition to the revision data, are put together to manage and track commonalities and execution of the projects. So we have revision data and put revision IDs, group numbers, and change numbers. And the union of these different groups they gives you what are common between different activities, different projects that you're tracking. The next thing about tracking managing a system through life cycle using revision data is really to go from the past, present, and future of the system. There are projects that starts from one time and finishes to some other time from past, and it was finished past. Projects that starts again, another project X that started from the past, but now in the present we would merge it to another project, and we merge it to the base data, which we call as built, and we have another one that goes on for the future. The whole thing is that you want to keep track of every one of these projects at what has changed and what's included in those projects as far as the data and the elements that was changed forever in the same database. So revision data is an advanced management tool to create, merge, compare, delete, or whatever you like to do based on revisions, group numbers, and change numbers. So if I look at the project with the base data, which is again as built, and you have a bunch of revisions, the idea is to be able to merge these at any one time you want and in any fashion you like, and then do the analysis for each one of them and see the effect of one revision or combination of revisions together. So you can do analysis at any one time between different revisions of the same power system, all in one database. So the next is generation. Generation level changes in the system, and generation level might change for different purposes, especially in renewable system that you have WTGs and solar units, which can be minimum, maximum, or zero, or whatever value they can be. So we provide different layers of generation level, and this is during the design, it would be assumed values, or during the real time would be operating, and the playback would be whatever it's been recorded before. The next element is loading data, which for different studies you have different loading data, minimum loading, maximum loading, and so on, and normal loading during the emergency loading. So with that we also have different values. And remember again that during the design you don't have the actual loadings, so that you would have assumed values and you have to do number of studies at different loading conditions. And you want that the program remember all these loadings that you're going to be doing, assuming. But real time also you have operation, and then you have the archive data to bring up and see what has been done, had been operating before of loading and generation. So these are the 3 dimensions. The next dimension, the 4th dimension, is configuration. This is the status of the system and modes of operation of the elements. For example, circuit breakers can be open or closed. Switching devices can be open or closed. They can be in different positions if there is a transfer switch. Cut jumpers, you have reclosers. Then you have motors, which can be continuously operating or intermittent or spare. Or you can have open or closed or throttle motor operated valves. You have UPS the same way. Generators can have modes of operation, swing, voltage control, megabar, and power factor control. Inverters can have modes of operation from grid forming, voltage, megabar, and power factor control. Same thing with WTGs, and capacitor can be continuous or switching capacitors and so on. Next, we're going to talk about configuration. That is the operating status and modes of operation of different apparatus of the power system. For that, we call it the status, and that would be unlimited number of configurations. And again, during the design, we have to assume, we have to combine different configurations to have the worst conditions for load flow, for short circuit, and so on. And then you have real-time operating status of the equipment and real-time archive data that you can bring up and see what has gone up in the system. The next is view and visualization of the system. In ETAP, you have multiple or unlimited number of presentations and visualization of the one-line diagram. And that is useful for different purposes, and also useful to be able to do simultaneous studies. Next, I'm going to be explaining the configuration dimension of the system. The configuration is right here in this particular one. It shows 3 configurations. One is called normal, and you can see this presentation. When I change this to TS event, this portion of the system is de-energized. If I go to TS event, this portion of the system is de-energized. So with the 2 configuration that I have here, I can go to the configuration manager and can see the IDs of the element. If I want to see the different stages, I can see the different status of all these breakers, and you have as many as all the status of the motors and everything else, if they are, what mode of operation they are or what the status they are. If I want to see the change data or differences, I can see that the different elements which are in different positions. Now I want to go ahead and show you how to add a new configuration. You press new, and it has a new configuration, and let's call that Farouk's configuration. This way you're going to remember my name. So with that, I just added one, and this particular configuration shows the new configuration, and since this configuration is not checked, they're going to show all closed or different status, but it's showing unchecked essentially. So if I go back to the one-line diagram and I look at the configuration TS event or normal, if I go to normal, everything is normal here. If I go to this Farouk's configuration again, and I can open up the generator, I can open up this breaker here, and I can open up this breaker here. So I just de-energize this portion here. Notice the generator, since I did not create the generator in different status, so the generator is still operating but is not connected to the system. But my configuration is changed now. And remember, I had configuration of normal, everything was closed, of configuration stage 1, which is this portion of the system is open, and then TS event, that is this portion of the system is de-energized. So this is configuration. I can have now two different presentation, and that is the presentation, and that is the one I'm looking at is the study view. This one here is relay view, where I am showing the data blocks for different elements. I'm going to turn that off so you can see the system maybe more simpler, and I can go ahead and show you the difference between this system, but I'm going to put both of them in normal configuration for sake of simplicity. But notice that in this particular one, relay view, I'm showing all the protected devices. Well, in this one, I'm not showing them. But I can have a concept here, I can hide elements. And when I hide the elements, it just doesn't show anymore. But when I click on it, it shows a diamond. That means there is a hidden element in there. I can also hide this guy right here. So here I'm doing, for example, load flow studies. So I'm going to go to load flow studies and run load flow. And I can see the result. I'm going to close this log because it gives me element, the log of the alarms and so on. And you can see the result. I can, of course, display the different result in different units. I can go here and I can go here, this one here, go to the short circuit mode. And I can run device duty on the short circuit mode based on ANSI. The results are shown here now. And I'm showing here the result in load flow. I can do this in both of them in load flow mode and run different studies at different configuration. I can do any combination of things I want to do. But the trick here is that I run in simultaneous studies. And if I go ahead and change something here, let's say I change this generator from 7.5 megawatt, and I change this one to, let's say I change it to 30 megawatt. Just for the sake of changing it. So notice the result went away from both of them. Actually, the result become gray. That means these results were old ones. They're not applicable right now. I can run load flow here, and that is showing the new result, and I can run short circuit here, and I can see the effect of changing that to different values right away. But let's do another thing. Let's go ahead and go to this transformer and change the impedance of a transformer from 6.9%. I'm going to change it to, I don't know, 16%. I'm just going to have a hard time finding a transformer with that high impedance, but I'm going to do it just to make a point. And I can run load flow again. And I can see this bus right here went below 97% or 98%, so it's showing warming here. But I can run the short circuit here, and I can see that this particular fuse has a warning flag on it. So the point is, load flow wants to keep the impedances at minimum, so that the voltage drop are at minimum. Short circuit, on the other hand, wants the impedances at maximum because it limits the short circuit values. So these are pulling the system in different directions. But having them both next to each other can really run the studies simultaneously and see how the effect is at the same time. You don't have to do one and then change it to short circuit and remember what you have done in the other study. And that goes for any one of the studies here. The study toolbar allows you to do any kind of studies in any one of the presentation. And remember, you have unlimited presentation, unlimited configuration, and unlimited base and revision data. Now I'm going to be talking about the sixth dimension of the database, which is analysis, optimization, and solutions. And remember that for design, you have to do all these different loading, generation, configuration, or status configuration, base and revision data. For real time, you have actual operating data and the operating loading and generation. Now you don't have to assume them like during the design. And then you have to create different study options, different standards, different reports, different plot types, and then look at the result using plot analyzers, report comparisons, and then UD reports. But also, as result analyzer and plot analyzer are one of the nicest tools that you have to really compare different results in a glance. And study scenarios and wizard, which allows you to repeat the studies at any time you want by remembering the studies or things that you have done before. And then, of course, that repeatability of the scenarios gives you a chance to really look at what you have done, what all the studies you have done 2 months ago or 2 years ago, and you can repeat them again and come out with the same conclusion or different conclusions. So now the 6 dimensions is what we call solutions. And you have unlimited number of solutions that you want to have. And you can run them based on different configurations, different views, different loading, different configuration, different generation, and different revision data. 7th, 8th, 9th, 10th, and so on dimensions are hard to show now. This was I showed you 6 of them. But in reality, these dimensions states that's a time series concept, that the whole thing expands as per function of time. Then you have the operation values that can come in. Then you have states and service values. So you have all of these dimensions that really helps you to manage a platform that gives you flexibility to be able to run system studies, operate the system, automate the system for different conditions, and remembering the whole thing in one database, in one platform. So what are the other niceties of this platform besides this multiple dimensions? The main thing of this platform is, of course, the one-line diagram, which is unlimited presentation for simultaneous studies. You have abstract and logical views for like network view, feeder view, substation view, panels, GIS, safety systems, overcurrent protection, distance relays, arc flash, and ground grid, underground cable raceways and cable pulling, stability analysis, electromagnetic transient, user-defined dynamic models, parameter estimation, parameter tuning, and then co-simulation with EMTP, with Simulink and other tools for transient analysis or electromagnetic transient analysis. Train railways, relay views, and one-line view and GIS view, and control system logics, which I'm going to show you, and result with analyzers and plot and comparison. So these are one platform that handles that, plus SCADA, GIS, OLV, railway system, relay view, safety in real-time data. And that is a bit different track altogether, which is really not time to explain that, but those are all supported by the same platform. So the one-line diagram, you have the single phase one line, and with a capability of seeing the result in platforms live on the same one-line diagram. You have single phase diagrams, and then you have the geospatial diagram, which is also a one-line diagram but in a GIS format with all the latitude and all the dimensions and locations. Abstract views is the first one is network view. We call it net view, and that is really showing the substations, the connection of the substation without really showing the elements except switching devices. Then you have the substation view, and then you have feeder view in 2 different formats, which really gives you a very simple understanding of how the feeders are feeding the customers on the distribution side. The next set of applications that the platform supports, of course, are safety systems, and that is start with the protection and coordination, time crank characteristics, and all the niceties that comes with it. It works directly with a one-line diagram. You can create one and move them around graphically. Then you have the same thing for the arc flash hazard time crank characteristics. Then you have the distance relays or impedance relays that here are shown the X over R graphs. Then you have the ground grid, which is really IEEE and IEC standards, and also finite element method, which would for any configuration you like to have. But at the same time, it also works directly with ETAP. So it knows it can put in this under the substation, so it works with the short circuit values for the substation and does the analysis. Cable systems is the next set of applications we can utilize this platform. And I'm going to show you here that the same cable from one line diagram can be placed in an underground duct bank or an underground raceway, the direct barrage system. And you can run the thermal analysis on those, and it would be telling you exactly what the temperature is going to be and the effect on the adjacent cables and the different conduits or locations. You can also do the cable pulling from for the same cable you did the thermal analysis. You can do the cable pulling and get the maximum or minimum tensions or both ends, forward or reverse pull, or the sidewall pressures at different location and the bend, and it has no limitation as the slope and the angle of the different bends. Transient visualization views includes, of course, UDM, which is a logical block diagram. It has integrators, differentiators, adders, any kind of blocks that you can imagine that are there, and you can create different block diagrams for governors, exciters, for loads, for inverters, and you can run them along with as part of the transient stability, where you have built-in exciter governor or UDM exciter governor, or any kind of user-defined models that you have. Waveform recording is another one that we can record the waveform, do the analysis, find the fault location based on that. You can have the parameter estimation and tuning, which is very, very useful to tune the parameters of your exciter governor and the generator themselves to come out to match the test measurements that you have done in the field. Train animations are really one of the niceties about eTracks. It shows the movement of the train. Those trains that is shown in red are not really choo-choo trains. They are high speed, high voltage, AC or DC trains with showing the actual tracks here and showing the substations, the configuration. You can zoom in, of course, you can see more details. This particular one is a DC track. And you can see the same movements of the trains on the GIS view. Next is control system animation view that shows the animation of a control relay, different type of elements in there. The whole thing is really based on the actual configuration of the operation of the system and configuration of the system and the different conditions. In this particular one, these switches are being pushed, and then as a result of that, other relays operate and other relays get operating. And the nice thing about this is that you can get the voltages at different points on different systems, different branch, and see the flows of everything in there at the instant that these are configuration change, and make sure that the relay system works. Real-time operation view is next, and that is really the SCADA view, the one line diagram, which can see the result on the one line diagram, network view, and also substation view. Project management execution is the last item that I want to explain, and that is really the challenges of doing all of these capabilities that we have in the ETAP digital twin platform. But what are the challenges in management and execution of projects? So first is the field data collections, and that is data entry. Next is project delivery time, and that is network project modeling and management utilizing NetPM. Next is the speed and efficiency, which is important to be automated with automated layout, validation, and templates that ETAP provides. And then solution reliability, which I explained at the beginning. We are a nuclear verified and validated software and libraries. This is the high impact software, the first one in the world, the only one in the world in power systems. Consistency of the solutions, which is intelligence, rulebook, libraries, and warehouse, and transition to real time. And that is really important. So because you go design a system, you have the model, you validate the model and all that, but then you want to go to real time. You have to just add the real time data with a very powerful integrator that you can select and pass the data from real time to the model, and you have an operational model. Simple as that. So you have model-based operation model that it can predict system behavior, can do many other things, which you can go through different locations in ETAP website and see all the capabilities we provide. So the data collection and verification ETAP app, you can run it in any tablet, and you can create one-line diagram or bring the one-line diagram from ETAP. You can change the data and pass it to ETAP, or you can take pictures and pass it to ETAP, collect data, and with the location based on GIS point, and pass it to ETAP. Next is NetPM. NetPM is probably one of the best tools for engineers to collaborate and do parallel project executions. It would shorten your project execution time, faster delivery time, increase design quality, improve productivity, optimize project resources, and all with having one centralized ETAP platform. All the other guys in different locations, in different time, they can, or simultaneously actually, they can run different studies, they can change the system, and all their changes going to come through the NetPM and distribute among everybody in the system. So you can put it in auto mode or on-demand mode, and you can get the changes from the other engineers working together. To show you the benefit of NetPM, I'm going to be showing you first project management and scheduling without NetPM. That is, you start having one engineer doing modeling by himself, then you have another engineer or same engineer. After it's finished that, it continues with model validation, and then run load flow, and then run short circuit, and then run selectivity or coordination analysis, arc flash analysis, motor starting, harmonic analysis, transient stability analysis, and then load sharing analysis. And it takes him, maybe in this particular project, it starts from the beginning of the year, and it goes all the way to 10 months later. He's finishing 10 months for this project. But if he can have simultaneous modeling, studies, and validation, and so on, we would reduce the time to half as much. Instead of 10 months, it would take 5 months. And if you really want to do this better, you can do it faster, because the nice thing is that modeling, you can do multiple ones at the same time. You can do the validation at the same time. You can do the load flow short circuit. Different engineers running their studies at the same time. It's a big system, and they run their studies and they can collaborate together. Same thing for the coordination and arc flash, because coordination and arc flash, they go hand in hand, right? And then motor starting and transient stability, they can start doing all of them at the same time. So they can use a centralized database which communicate between all the engineers. You can have 10 engineers working on one project at the same time. They can do any method that they want to work with. And it's more effective because it's collaborating with each other. They're learning from each other and knowing what pulls the system in one direction, another thing takes it in the other direction. It combines all of the efforts together. So with that, I'm going to go ahead and finish up this platform, showing you the different things that we discussed: revision data, going to generation, loading, and then doing visualization or configuration, and then visualization, and then the solution it provides, and going with the time, operation, states, and services that creates the entire system of the platform, which support all the functionalities, all the solutions from ETAP. So ETAP accelerates energy transformation, and that is really the guts of the matter here. We can design and operate using the same platform, and it's really the beauty of it, that you have a platform for operation which is model driven, and you have done all the design based on that. And during the operation, if the model changes, you can update the model again as a matter of the click of a button. So the number of multi-phase process is plan and model, design and analyze, build and commission, manage and operate, assess and maintain, transform and grow, and decarbonize for sustainability of the system. So this is really the entire process. The purpose of all this, what is all of this comes down to, is really to ensure the facilities remain efficient, sustainable, and available throughout their life cycles. What we do with the unified intelligent platform is essential to do this. You have faster planning and modeling, accurate design and analysis, confident build and commissioning of the system, intelligent management and operation, connected assessment and maintenance, informed transformation and growth, and finally, adapt renewables and decarbonization in the whole project that you have. So with that, ladies and gentlemen, I like to thank you for listening to my presentation, and I encourage you to go to etap.com for any questions you have. You can find many different descriptions on the solutions and the platform that ETAP provides. And if you have any other questions, you can call ETAP, the sales department, or the engineering division, and get answers to your questions. Thank you very much, and God bless.